Hi everyone. Alright, today we're going to delve a little deeper into plate tectonics by looking at the plate boundaries and the forces that move these plates around. So let's start by going to the page of your dynamic crust packet that looks like this, which right now would be page 10. And also please have your ESRT open to page 5. And let's take a look at these things right now. So we have different kinds of plate boundaries. Just to kind of back it up a little bit, if you're going to have different plates, let me show it with this one here, because we're familiar with this one. If you're going to have different plates, then you're going to have boundaries between those plates. And those boundaries are going to be places where those plates contact each other, and there's going to be different kinds of motion going on there. So let's take a look at these boundary types. So the first of the three types of plate boundaries that we can have is called a divergent boundary. Now for things to diverge, that means they have to move apart. So the plates are moving apart from each other, and here's what I want you to know. All mid-ocean ridges are divergent boundaries. Okay, the Mid-Atlantic Ridge, the East Pacific Ridge, and so on, all these Mid-Atlantic ridges are divergent boundaries. One of the ways scientists located these and discovered these was just simply dragging a thermometer in the deep ocean past it. And when you drag a thermometer past it, the temperature goes up. So there's something hot coming out here. So what's happening here is out of this rift in the middle of this valley, you have that molten rock from inside the earth coming up, and it's hot. It hits the cold water and it cools and becomes hard igneous rock, and the plates move apart. Now, this type of boundary here looks on the map like this. This is the symbol you'll see on your page 5 of the Earth Science Reference Tables, except it'll have a couple of little arrows which you'll need to put in right now. So you have a couple of little arrows right here, and those arrows indicate that it's moving apart, and this is the symbol for that. So that symbol represents this divergent boundary right here. So on your ESRT, just a quick look-see. So you look around, these are the symbols we're talking about, right along here. East Pacific Ridge, right there. Southeast Indian Ridge, right here. And your Mid-Atlantic Ridge, these are all the divergent boundaries we're talking about, where those mid-ocean ridges are. Now, I'm going to show you quickly a little animation to sort of make this come alive for you. So let's take a look. Here is an example of a mid-ocean or a divergent boundary, mid-ocean ridge or divergent boundary. Watch carefully. Hot magma's coming up, melting the rock in here. I'm sorry, magma comes up, turns to lava right here, and out gets pushed the two layers of the oceanic crust. So take a look again. Fresh material comes up, forms new rock here, and out goes the lithospheric plates from the center. They move apart right there. Okay, I think we're okay with that. Now, I have one little question to ask you. It's going to be kind of like a scavenger hunt on page 5. I told you that all mid-Atlantic or mid-ocean ridges are divergent boundaries, but which continent actually has a divergent boundary in the middle or in it? So I want you to look around in the ESRT for a second, and I want you to locate which continent has this type of boundary in it on land. All right, well, you've searched and searched, I hope. You've looked around, and where do you see those two arrows happening on land? Only here, right there, Africa. Africa has that divergent boundary on land. Africa is actually splitting in half right there. Okay, very interesting, very, surprising. Okay, Africa would be your answer. Now the next type of boundary, very exciting type of boundary, is the convergent boundary. Now when you have a convergent boundary, the plates are moving toward one another. All right? Sometimes these are called collision boundaries. They're sometimes known as collision boundaries. So the plates are moving toward each other, into each other, and they're colliding. Now, take a look at the diagram down here. Here's one plate, here's another plate. These plates are moving toward each other, and one plate is going under the other one into the earth. All right, now let me make this kind of come alive for you. Let me show you this in an animated fashion. So here is your convergent boundary. See the two arrows? The two plates are moving toward each other, but they're not going to have a big pile up. One's going to go down beneath the other. Now watch this happen. So this plate is going down into the earth, and it's melting down here in the asthenosphere, and that's creating volcanoes up above. Now people, this is a really important word. This sinking into the earth is known as subduction. This is called subduction. So this would be called the subducting plate. This plate is not subducting, so we're going to call this plate the overriding plate. So you have a subducting plate going down and an overriding plate. So let's put this down here. Blank is the sinking of one plate beneath another. I just told you. Please put the answer down. And the answer is subduction. Okay, so here's an example. If you look at this diagram, we have oceanic crust right here converging with continental crust. Oceanic converging with continental. Now, I want you to stop the video for a minute and go to the ESRT, look for this symbol, and find where you can find oceanic crust colliding or converging with continental. Find me a place where that's happening. Okay, well, hopefully when you went to your ESRT, let's see, here's convergent with ocean on both sides. That's not going to work. And here's convergent with ocean on both sides. So I would say your best example would be right along here. The Peru-Chile Trench, where the Nazca Plate meets the South American Plate. There's oceanic crust colliding or subducting beneath continental crust right here. The oceanic meets the continental. They converge right along the Chile-Peru Trench. Okay, so I'm hoping that you said the Chile-Peru Trench area. Okay, so now let's take a look at the diagram one more time. We have two plates. Here would be your South American plate. Here would be your Nazca Plate. Here's your convergent boundary where the trench is. Which of these two plates is the subducting plate and which is the overriding plate? What do you want to call this one right here? Please put your answer right in here. Is this the subducting plate or the overriding plate? Well, the answer is this is the subducting plate, and therefore this would be the overriding plate. All right? This is how it's shown on the map. The subducting plate is behind the blocks on the symbol, and the overriding plate is in front of the blocks on the symbol. Okay, let's continue. Time's getting short. Okay, let's move along to our next type of boundary. Well, actually the same type of boundary, just a different example of it. So we can have convergent boundaries. We can have convergent boundaries where it's oceanic crust meeting oceanic crust. So take a look up here. Here's oceanic crust meeting oceanic crust. Oceanic, oceanic, and the oceanic is subducting beneath another oceanic. Okay, that happens out there a lot too. So example 2, we have oceanic crust converging with another oceanic crust. Now, let's just quickly go to the ESRT and find an example of that happening. I just inadvertently showed you 2 of them. Pause the video, check it out. All right, so oceanic converging with oceanic. Well, it looks like we have one right here by the Aleutian Trench. Looks like we have one here at the Tonga Trench. Looks like we have one here at the Mariana Trench. All these are examples of oceanic subducting beneath oceanic, converging with another oceanic right there. Okay, looking good. So, let's take a look at let's take this back to our notes for a moment. So, an example you could have chosen, I'll have to accept a few of these. You could have chosen the Aleutian Trench, the Mariana Trench, or the Tonga Trench. All have that. Now, again, it also produces volcanoes just like the other one did, except these volcanoes stick out of the water. All right, so you have volcanic islands that stick out of the water. Very, very beautiful, but very dangerous. Now, our third example of a convergent boundary would be when continental collides with another continental. So you've got overriding and subducting just like this, but you've got a continental plate colliding with a continental plate. Please go to the ESRT and find one of those real fast. And if you did, hopefully you found right here where the Eurasian plate meets the Indian-Australian plate. That's where continental, this is all continental, this is continental right there, see the color? They're colliding, and that's producing the tallest mountain range in the world. There's a huge pileup happening right there. That's producing the Himalayas and Mount Everest. So your answer for that one would have been a little harder to write down, but that particular convergent boundary would be the Eurasian Indian-Australian plate meeting at 30 degrees north and 80 degrees east. And again, we have a subducting plate and we have an overriding plate, but this produces quite a mountain range. Okay, last plate, or last collision, last border, boundary. So here we have our transform boundary. Now in a transform boundary, the plates are sliding past one another. All right, they're sliding past. So quick pause, go to the ESRT, find one of those, put it down right here. Okay, so you went to your ESRT, you looked around for one of those, and I'm guessing you probably settled on the San Andreas Fault. That's the most famous one in the world, produces all those earthquakes that we have in California. Okay, so hopefully you said the San Andreas, but if you said something by the Scotia plate or by the Sandwich plate, I would have accepted that too. Okay, but of course, usually when, the easiest one to mention, the most famous one, would be the San Andreas Fault. And finally, what causes the plate motion? Well, let's take a look at what's causing the plate motion. And this is going to be a slightly different diagram. I'm going to have to go to a different diagram for everyone. What's happening here is this. Your diagram looks like this one right here. So what's happening is this. Let's take a quick look at page 10 of the ESRT. Notice in the asthenosphere, we have that material, that plasticky rock material, is moving in a circular pattern like this. It's going to sink, and then it's going to rise again. And it goes round and round. That is what we call convection. We see it in the atmosphere. You can see it in a hot cup of soup. Convection, up and down. Now what happens is, when this material rises up here at that break in the ridge, that new material is going to come up in here, and this ridge is going to get pushed out this way and this way. All the way over here, where the material is returning deep into the earth, sinking down like that, that's when the plate subducts down into the earth like this. So when the two convection cells converge right here, that's when you have your subduction down into the earth right there. And when the two convection cells have a divergence here like this, moving apart, that's when the ridges get pulled apart or pushed apart, and here the ridge gets pulled, the plate gets pulled down into the earth by the subducting plate right there. So learn to recognize where that is. Let's take a quick look. Our video is running a little long. Please draw this better than I do. Here's where the material is, here's where the material is, yes, coming up right there. The material is coming up right there. And the material is coming down right there. And it's coming down right there. And you can finish your pattern like this. And you can peek at your ESRT to see how it looks on page 10. Okay, so there's your convection pattern. Now what's happening on the surface? This is causing these two plates to move apart right there. That's your divergent boundary. And here's where your two plates are coming together right there. That's your convergent boundary. And here's your other convergent boundary. Okay, so to get that into something we can write down, you can pause the video. What's happening here? Convection, this motion, is the driving force. The convection is the driving force right here. Okay? So hot, less dense material rises, and then it loses its heat, and it becomes more dense, and it sinks. The resulting material causes this pushing and pulling. This motion causes the pushing and pulling of these plates, and it causes the plates to move. And all this is because of this tremendous heat down here coming out of the core, or coming out of the stiffer mantle actually, and producing all this heat here, causing this to circulate in the asthenosphere. Okay, have to pull the plug on the video right there. Thanks for paying such good attention, everyone. We'll have some questions later.